Hi, I'm Himanshu,
I'm Aname.
and today we're going to be solving this problem and studying the basics of operational amplifiers.
Before we solve this problem, it is important to understand what operational amplifiers do. What operational amplifiers do is they take an input voltage across two terminals, a negative and a positive terminal, the potential difference across those two inputs, and create an output that is a multiple of the input value. So usually what operational amplifiers does is there's a V out that is a gain factor of a V in. At this output, at the input terminals, there's zero. There's a high level of impedance, which means there's zero current going through this terminal. But at the output, there is a very low resistance, so there's a very high value of potential coming out of it. So it takes two input values and gives us a single output value of a significantly high potential difference. This circuit in particular is an inverting voltage amplifier. What that means is, usually when you have a operational amplifier with just a single output and two inputs and nothing else connected to the output, you have something called an open loop. The thing about an open loop is like our gain value can be as high as infinite, thousands of values higher than the thousands of multiples of the V input will give us the V output. In order to create a stable operational amplifier, we want our gain value to be controllable. And to do that, what we do is attach a negative feedback to our operational amplifier, which is what inverting amplifiers do. So what we do is attach a negative feedback, which means attaching a resistor from the output value back to our negative part of our input values. The reason why we want this at the negative terminal is we want to take some of this output and include it back in a negative form for the potential difference across both input values. For an inverting amplifier, what this does, it helps to control our gain value because we take out some of that input and then we can get our gain as a function of the negative feedback that we have put into our circuit. My teammate Himanshu is going to be talking about the differences between inverting amplifiers and non-inverting amplifiers.
Okay, so let's look here at the graphs. For non-inverting amplifier, okay, so if the source is like this, for inverting ones, the phase changes 180 degrees and this comes down, it goes up and this goes down like this. So this is inverting amplifier for inverting amplifiers, since the phase changes in input and output, and the amplitude can increase because it's an amplifier. So you gain the amplitude, or you can maybe decrease. And and if you want to increase the amplitude without actually changing the phase, then we have non-inverting amplifiers. And for non-inverting amplifiers, the graph remains the same. Like the phase of the graph remains the same while the amplitude changes. So this could be like this. So that could be this. And it could go like, the amplitude changes, so it could be this, this, and this. So you can see the amplitude changes, but the phase remains the same. So that's for non-inverting op-amps. So now we're gonna come to this question number 1 of homework 8 and solve that step by step. Okay. So what do we have here? We have VP, we have Vn, we have Vo, and we have this. So first we are going to figure out what Vp and Vn are. that, we need to solve this part of the circuit. So if you look here, we don't have anything between these. So this is VP as well. They are the same potential because there's no potential drop across this area. So doing doing NVM here, VP upon 10,000 into 10 raised to the power 3, because 10k minus 0 plus VP minus 5, because we are going this side, so it's VP minus 5 on 20 into 10 raised to the power 3 is equal to 0. That's according to our NVM at node VP. So VP into 2 plus VP minus 5 is equal to 0. So 3 VP minus 5 is equal to 0. VP is equal to 5 by 3 volts. So VP is equal to 5 by 3 volts. So Vn is equal to VP in ideal conditions. So Vn is equal to 5 by 3 as well. So doing NVM at Vn, we have Vn minus 0 from 10 into raised to the power 3 plus Vn minus V naught by 20 into 10 raised to the power 3 is equal to 0. So when we solve this, we have 2Vn plus Vn minus V naught equal to 0. So V naught is equal to 3Vn, which makes V naught 5 volts. So looking at the question, we have 5 different parts of this question, which are find V naught. We already have V naught, which is V naught is equal to 5 volts. We have VP. VP is 5 by 3. VP is equal to 5 by 3 volts, which is 1.666 volts. We have Vn, which is equal to VP. We have I naught. So the fourth part of this question, the last part, is find I naught in mu amperes. So mu amperes, microampere is 10 raised to the power minus 6 amperes. So what's I naught? I naught is this. So for I naught, we need to do VP on 10 raised to the power 10 into 10 raised to the power 3. So this becomes 1.66 on 10 raised to the power 4. So that becomes 166 into 10 raised to the power minus 6 amperes, or is the 166 microamperes. So the fourth part's answer is 166 microamperes, and that's an inverting amplifier. And then the gain this is V naught by Vs, or minus RF by RS. So coming to and comparing that with non-inverting amplifier. So this is the example of a non-inverting amplifier, and in this we can see that the voltage source is connected to a non-inverting input, which is positive, and in the same thing we still have the V naught going to the inverting input. But if we solve this, we have Vp is equal to Vg, because there is no current going here, because of ideal conditions. Under ideal conditions, this has infinite impedance, so we don't have any current going in. So Vp is equal to Vg is equal to Vn. doing NVM here at Vn, we have Vn minus V naught upon Rf plus Vn upon Rs is equal to 0. So Vn minus V naught into Rs plus Vn to Rf equals 0. And so on solving this, we have Rf Vn plus, we have R V naught Vn Rf plus Rs minus V naught Rs is equal to 0. So Vn Rf plus Rs is equal to V naught Rs, and V naught upon Vn becomes Rf plus Rs upon Rs. So that's the gain for our inverting input, a non-inverting amplifier. Yeah. And I'm comparing that with an inverting amplifier. The gain is for that is minus Rf by Rs. So we can see that the phase changes in an inverting amplifier while the phase doesn't change in non-inverting amplifier, and that is a basic difference between a non-inverting op amp and an inverting op amp. Thank you.